of optical signals inside a planar waveguide. So we solved, in fact, we derived a particular equation for the electric field, which was written in this particular form. So A cos kappa into d by 2. So A cos kappa into d by 2 is equal to B into exponential minus gamma into d by 2. So this was the in fact, this was the equation for the electric fields. This was the eigenvalue equation for the electric fields. Now similarly, in the case of you can do the same exercise for the magnetic field, and for the magnetic field you will be having a continuity equation of this form: A kappa into sine kappa d by 2 is equal to gamma into B into exponential minus gamma into d by 2. So the other one for the electric field is going to be A cos kappa into d by 2 is equal to B exponential so B into exponential minus gamma into d by 2. So this is the continuity. So this is the continuity equation for the electric field. So this one you call it as continuity equation for electric field. Now these two equations, so the one for the electric field and one for the magnetic field. So instead of using, so these two equations can be you can represent this by in the form of a matrix, because we have these two constants A and B, and all the other parameters, they are dependent on the waveguide. So kappa and D and gamma, they all are waveguide dependent. It depends on the parameters of the waveguide and also the wavelength at which you are operating. So I would represent these two equations. So these two equations by in the form of a matrix. So in the if you are using matrix, so matrix representation can be done like this. So if I use matrix, it looks like this. So you have cos gamma into d by 2 and minus exponential minus gamma into d by 2, and then here you have kappa into sine, sorry, this is kappa. So kappa into sine kappa into d by 2, and then minus gamma into exponential minus gamma into d by 2. So this multiplied by A and B, so this is going to be 0. So I'm just representing this by a matrix, so it's nothing complicated. So what I have done is, so I have left hand side is equal to right hand side. So I'm just taking the right hand side to the left hand side and then equating that to be 0, and then just I'm writing it in the form of a matrix. So if you have a matrix of this form, then you are trying to find the solution. So if A and B so one trivial solution for this is, the most trivial solution is A and B to be 0. But A and B to be 0 is the trivial case, but we are not interested in that case, because if A and B is 0, then it means that there's no wave and there is no waveguide, which is not interesting. So what we are going to look is, we are interested in looking at non-zero solutions. So to find the non-zero solutions, So to find the non-zero solutions, so the condition so that this matrix can have non-zero solution is that the determinant of this matrix should be 0. So that is one way of saying. The other way is you can simply divide these two equations. So you can even simply divide these two equations. So if you do that, you're going to get this particular relation. So if let's say that I'm going to calculate the determinant of this matrix. So I'm going to get minus gamma exponential minus gamma into d by 2 cos kappa into d by 2 plus exponential minus gamma into d by 2 into kappa into sine kappa into d by 2. This is equal to be 0. So if I further simplify this, then I am going to get this equation. So kappa into tan of kappa into d by 2. So kappa into tan of kappa into d by 2 is equal to gamma. So you get this relationship. So this important relationship, so this is what is called as the eigenvalue equation. It's called as the eigenvalue equation for a symmetric waveguide. So this is the eigenvalue equation for the symmetric waveguide. So if you recall, kappa is given by k naught square ng square minus beta square. So kappa is k naught square ng square minus beta square, and gamma is root of beta square minus k naught square n square. So I have used this word, I have used this symbol n, where this n indicates, so n indicates the refractive index of the cladding of this cladding. So this cladding could be the top cover layer or the bottom substrate layer, but we have assumed that this is a symmetric waveguide, which means the refractive index of the top cladding layer and the bottom cladding layer is the same. So therefore, instead of using two symbols, I am just using this as n, just using a single symbol. So k naught is given by 2 pi by lambda naught. And what is lambda naught? Lambda naught is the wavelength of the light or the wavelength of the signal that is flowing through this waveguide. So for a given waveguide, you will be knowing what is the wavelength what you are launching. That means lambda naught is known, and as a result k naught is also known. If you are making a waveguide, you would obviously know what is the co-refractive index. So Ng represents the guide refractive index, or also called as the co-refractive index. So since you are the one who is going to design the waveguide, you will be knowing what is the guide refractive index. You would also know what is the cladding refractive index. So if you look at kappa and gamma, you would see that you know what is k naught. K naught is known, Ng is known, N is known. The only unknown remaining is beta. And what is beta? Beta is the propagation constant of the wave that would be supported by the waveguide. So beta is the propagation constant. Is the propagation constant of the wave that will be supported by this waveguide. We were talking about the TE mode. So for a TE mode, the beta what we are going to find would be the propagation constant of the TE mode. If the waveguide is going to support only one TE mode, then that beta, the beta what you are calculating would be the propagation constant of the TE mode that is supported by this waveguide. So we are essentially interested. So if you look at this eigenvalue equation, we are essentially interested in calculating what is beta. So beta is the only unknown parameter in this equation. So the left hand side and the right hand side, beta is the only how to say, beta is the only unknown. So that is what we are interested in calculating. So, so what we would do is, so I would slightly try, I would rewrite this equation. So you have this equation, kappa into tan of kappa into d by 2 is equal to gamma. So I'm now going to multiply the left hand side and the right hand side by d by 2. So I'm going to write, so gamma into d by 2 is equal to kappa into d by 2 into tan of kappa into d by 2. So this is the same as, so gamma into d by 2 is the same as, so what was gamma? So gamma was root of beta square minus k naught square n square. So that means gamma into d by 2 is equal to d by 2 multiplied by root of beta square minus k naught square n square, which is the same as root of, so again I have d by 2 outside, which is the same as beta square minus, so I have this k naught square n square, k naught square n square. What I'm going to do is I'm going to add and subtract k naught square ng square. So I'm going to add k naught square ng square. I'm also going to subtract k naught square ng square. So nothing changes. The equation all remains the same. So this is the same as, so I'm still going to modify this. So this is the same as, so this can be written as, so I'm going to take d by 2 inside the bracket. So therefore it becomes beta square d square by 4 minus k naught square n square d square by 4 plus k naught square ng square d square by 4 minus k naught square ng square d square by 4. And this can be further written as, so in terms of kappa and gamma, so this can be written as, so I'm going to slightly modify this, the same equation, but I'm going to slightly rearrange the terms. So I'm going to write it as k naught square d square ng square by 4 minus k naught square d square n square by 4 minus k naught square d square ng square by 4 minus beta square d square by 4. So I have this positive beta square d square by 4. I'm just rearranging these two terms. So I'm pairing these two terms. I'm pairing this term and this term, and I'm pairing this term and this term. That's all I have done. So I get something like this. Now, so now what I'm going to do is this k naught square d square ng square minus k naught square d square n square. So I'm going to define a new parameter called as v. So v is defined as k naught into d into root of ng square minus n square. So v is equal to k naught into d into root of ng square minus n square. Therefore, v square becomes k naught square d square into ng square minus n square. So if you look at this term, if you look at these two terms, this would be, so according to this new symbol, this term would be, this would be v by 2 the whole square. This term would be v by 2 the whole square. And what is this term? So we already know that kappa is given as root of k naught square ng square. So k naught square ng square minus beta square. And what we have is, you have this by 4. The 4 is a scaling factor here. So that this term, according to this definition, this term is going to be kappa into d by 2. So kappa into d by 2 the whole square. So therefore this becomes root of v by 2 the whole square minus. So instead of, so kappa into d by 2, I'm going to define this as, so kappa into d by 2, I'm going to define this as capital K. I'm going to define this as capital K. And therefore this term becomes, so root of v by 2 the whole square minus capital K square. So this was what? So root of v by 2 the whole square minus k square was nothing but kappa into d by 2 into tan of kappa into d by 2. So we have already defined what is kappa into d by 2. These two terms we have already defined. And what is that? That is capital K. And therefore, this equation becomes, so v by 2 the whole square minus capital kappa square, that becomes capital K into tan of capital K. So, so this equation, you call it as the eigenvalue equation. You call it as the eigenvalue equation, for the symmetric TE mode. For the symmetric TE mode. So you call this as the eigenvalue equation for the symmetric TE mode. So k into tan k is equal to root of v by 2 the whole square minus k square. So though we have defined new symbols here, k, so capital K and then capital V. So though we have defined new symbols, so it's all basically related to the waveguide parameters. So V is nothing but k naught square, k naught into d into root of ng square minus n square. And kappa is also defined in terms of, the waveguide parameters. So this equation, so again, if you are, so whenever you are trying to solve this equation, ultimately you are trying to solve what is beta. Because if you plug in all the values, ultimately you are going to, the only unknown that is remaining would be beta, which is nothing but the propagation constant of the waveguide. Now this equation, you cannot directly solve this. So this equation, so these kind of equations are called as transcendental equation. So the best way to solve this equation is by using the numerical techniques. So you cannot have an analytical solution, but you can solve it either by numerically or you can solve it graphically. So suppose, for example, if I say that you have an equation y is equal to 3x, or let's say that you have an equation sin x is equal to x. So sin x is equal to x. So one way of solving this equation is, so how do you solve this equation? Let's say graphically, if you want to solve this equation, graphically is much simpler. So how do you solve this equation? You plot sin x, you plot the graph of sin x, you also plot the graph of x. So you plot sin x and then you plot what is the graph of x, and the intersecting point is actually the solution of this particular equation. So we do the same process here also. We plot the left hand side and we plot the right hand side. The intersection of these two curves, of the right hand side and left hand side curves, would tell you what is the solution. In fact, that would tell you what is beta. Okay, so before we do that, let us once again go through the eigenvalue equation for the anti-symmetric mode. So this solution, what we have done, so what we have carried out so far is for the TE symmetric mode. It's so what we have done is for the TE symmetric mode. So how do you call a mode as a symmetric mode? So what is a symmetric mode? Can anyone answer this? Nishant is there? Nishant? Is he present or absent? Nishant? So what do you mean by symmetric mode? Can anyone answer this?
The electric field will have cosine profiles.
So field will have a, so what kind of profile?
Cosine.
Okay, so if you have an even profile or if you have a cosine profile, you if the mode is having a cosine profile or an even then you call that mode as the symmetric mode. So in deriving all these equations, we have initially assumed that the electric field, so we had assumed that the electric field inside the core is having a cosine profile. So we began all this exercise by assuming that the electric field profile inside the core has a profile of the form A cos kappa x. Then you call it as the symmetric mode, A cos kappa x. Rather, if you assume that the solution has the form A sin kappa x, then you have the antisymmetric mode or the odd mode. So if you do the same exercise, instead of A cos kappa x, if you just substitute it by A sin kappa x, if you do that, then the eigenvalue equation what you are going to get, if you do the entire exercise, the eigenvalue equation what you are going to get would be of this form. So instead of root of, so for the antisymmetric mode, so for the antisymmetric mode, the only assumption is that use sin kappa x instead of cos kappa x. So if you do that, then the resulting eigenvalue equation turns out to be like this. So minus capital K, so minus capital K cot K. So minus capital K cot K is equal to root of V by 2 the whole square minus capital K square. So again we have defined what is K and what is V. The same definition. All right. So now we'll try to plot these two equations. So one is minus K cot K. The other one is K tan K. K. So K tan K is equal to root of V by 2 the whole square minus K square. So this is for the anti-symmetric. This is for the symmetric mode. So we will do a graphical analysis. So just a second. So are you still able to see the screen?
No.
No, sir.
Okay, can you see now?
Yes, sir.
Okay, fine. All right. So what we are trying to do is we are trying to solve the eigenvalue equation. So I have written the two eigenvalue equations here. So this K tan K, this is for the symmetric mode. So the red one is symmetric. The blue one is the anti-symmetric mode. So that means here the electric field had a profile cos kappa x. Cos kappa x, and here it had a profile sine kappa x. So this root of v by 2 whole square minus k square. So this, the one which is there inside the square root. So this has a form. This has a this is the form of a. This is the equation for a circle whose radius is given by v by 2. So on the y-axis, what I am plotting is v by 2. That is there on the y-axis, and on the x-axis I am plotting k. So x-axis is k, which is equal to kappa into d by 2, and this one is v by 2. And what was, and you know what is v and what is kappa. So if I am plotting root of v by 2 the whole square minus kappa square, so then this equation, so this right hand side, okay, let us look at the left hand side. So this k into k into tan k. So the plot of tan k is something like this. This solid line corresponds to the plot of k tan k, and this dotted line corresponds to the plot of this cot k curve. So one is tan k curve, the solid one corresponds to tan k curve, the dotted one corresponds to cot k curve, and the right hand side, which is root of v by 2 the whole square minus k square, so that represents a circle, and this one is plotted by this circle. So you will see that these two curves intersect at certain points. So this is one intersection, another one here, so another one there. So you can extrapolate this. You can extrapolate this on the x-axis. So it's going to intersect at some point. So what will you get at this point? So at this point, you will be getting what is capital K. And what was capital K? Capital K was kappa into d by 2. So let's say that you have a particular waveguide. It has a certain dimension t. It has a certain ng. It also has a certain n. So this is the thickness of the waveguide. This is the core refractive index. This is the cladding refractive index. You also know what is the wavelength of the light that is passing through it. Now you are interested in calculating what are the propagation constants of the modes that can be supported by this waveguide. So you want to find out beta. So this is how you do it. You plot these two equations, you find their intersection, you bring it down, you can get what is capital K. And what was capital K according to our definition? So what was capital K? So capital K was kappa into d by 2. So capital K is given by kappa into d by 2, which is nothing but, and what was kappa? Root of k naught square ng square. So root of k naught square ng square minus beta square. So this is the value of capital K, and this one turns out, so you will get this value. How do you get this value? Because you can extrapolate. So let's say this value is going to be, let's say 1.5. I'm just giving you an example. So I'm getting this value as 1.5. Now if you go back to your design, if you go back to your waveguide, you know what is K naught. What is K naught? K naught is given by 2 pi by lambda naught. 2 pi by lambda naught. So you know what is lambda naught because you are launching the signal, and therefore you know what is the wavelength of the light that is passing through it. You know that. Since you have designed the waveguide, you also know what is the co-refractive index Ng. So K naught is known, Ng is known, and you have obtained the value of this equation from this graph, which is 1.5. So all you have to do is you can easily calculate what is beta. And what is that beta? That beta is the propagation constant of the mode that will be supported by this waveguide. So this would be the first mode. So if you look at these intersections, you would see that this is the first point where it has intersected for this particular waveguide. So you have an intersection here, you have an intersection there, and so on. So the waveguide can support multiple modes. We'll see that. So for the symmetric modes, if you want to find the propagation constant, you will have to look for the intersection point between the circle and the tan K curve, which is the dotted, which is a solid line. So symmetric modes corresponds to, so this is symmetric. So symmetric, this is symmetric, this is also a symmetric, and this is an anti-symmetric mode. This is anti-symmetric. So which means that the propagation constant what you are getting will be the corresponding propagation constant for the respective symmetric modes, whereas this one would be for the anti-symmetric modes. So since K and beta, since they are related through, since K and beta are all related, you would see that for each value of K, which is a solution of the eigenvalue equation, we have the corresponding beta values. That means for this point you get the corresponding beta value. For here also you get the corresponding beta values. So that means for a given set of parameters for a planar symmetric waveguide, you can graphically solve the eigenvalue equation, and thereby you can calculate what is the corresponding propagation constant. Okay, any questions?
No, sir.
Okay, if no questions, I'll stop here. We'll continue the further discussion. So we'll see about, so how many modes can be supported by this waveguide and what do you mean by the fundamental mode. So all those things, there are many more details that can be obtained by looking at this this plot, this eigenvalue plot. So more details we'll discuss in tomorrow's class. Okay, I'll stop here. Okay, thank you all.
Thank you, sir.